Hello. In this lecture, we are going to look at the conditional distribution. We already know about conditional probability, right? If we have two events, uh, A and B, we usually talk about probability of A given B and also probability of B given A, right? Uh, for example, the probability of A given B is defined as probability of A intersection B divided by probability of B when probability of B is not equal to 0. Now we are going to look at a very similar idea, but for random variables, right? We can write down events in terms of random variables. In that case, we can talk about probability of one event given another event. But here we are going to look at the conditional distributions. When you have two random variables, we can talk about the conditional distribution of one variable given the value of the other variable. So, for example, suppose you have two random variables denoted by capital X and capital Y. Then we define the conditional distribution of Y given X is equal to simple X, capital X is equal to simple X. So that function will describe the distribution of Y when the value of X is known to be simple X. So it will provide information about the possible values of Y when X is fixed at a given value simple X. We can talk about this for discrete cases as well as continuous cases. Right? When both X and Y are discrete as well as when both uh, X and Y are continuous. So we will first look at the situation when both X and Y are discrete. Let capital X and capital Y be jointly discrete random variables with joint probability mass function given by this notation, P usual notation that we have been using, Pxy within bracket xy, and the marginal probability mass function of x is given by Pxx. Now let us consider a fixed value simple x such that the probability mass function at that point is not equal to 0, such that Pxx is positive. Then we can talk about the conditional probability mass function of random variable y when capital X is equal to that particular value simple x. So that is uh, uh, called the conditional probability mass function of y given capital X is equal to the value simple x. Right. So different books use different notations to denote this conditional probability mass function. For this lecture, I will be using this notation. This is one of the common notations. So this is this quantity here. Let me use my pen to explain this. So this notation here is the notation or the label for the conditional probability mass function of y given x, right? And then within bracket, we have two numbers here, simple y and simple x. So this is the value at which we evaluate this function. This is the value that the fixed value of x, right? So this is the actually this what this means is the conditional probability mass function of capital Y evaluated at simple y when this random variable is equal to this value. That is the meaning of this notation. Some books use this notation P, Y, and they write down the whole thing here as the function and then write down simple y. So in that case, this whole thing is the label for the conditional distribution function of conditional mass function of y given x is equal to simple x. And this function is evaluated at y. Actually, I prefer this notation because there is a different uh, conditional probability mass function of y for each given value of x, right? So, for example, we can talk about conditional probability mass function of x given x is equal to, say, 0. That will be one function. Another function will be a conditional probability mass function of y given x is equal to 1, right? Assuming that x can take value 0, 1, 2, and so on, right? So each of these are different functions. Similarly, you may be able to talk about y, conditional probability mass function of y given x is equal to 3, say, right? So for this function can be evaluated at some value y, right? For example, this is another function that is a different conditional probability mass function. You may be interested in evaluating that at value, say, 2, right? So we are looking at what is the probability. In this case, we are looking at what is the probability y is equal to 2 when x is equal to 1. In this case, we are looking at what is the probability y is equal to simple y when x is equal to 0, like that. So that is what we mean by the conditional probability mass function. So how do we get that answer? How do we calculate it? This is the definition or the way to calculate it. The probability, conditional probability mass function of y evaluated at simple y, given that capital X is equal to simple x, is defined as the probability, joint probability that capital X is equal to simple x and capital Y is equal to simple y divided by the marginal distribution of x evaluated at x, that is the probability x equal to simple x, right? So you'll see that directly there is a resemblance to the conditional probability idea. There we looked at probability of A intersection B divided by probability A, for example. Right? So this is again an event. This is also, and this event is the same as this event, right? So it's very similar to the conditional probability idea. Uh, but now we are writing the events in terms of random variables. Uh, if we use the probability mass functions, joint probability mass function and marginal probability mass function, we can write down this one as the joint probability mass function of x and y evaluated at x and y point, xy point, divided by, this is the marginal distribution, marginal mass function of x evaluated at x. So for this definition to be valid, this value should not be equal to 0. So that's why we have assumed that at value x, px is equal to some positive value, right? If px equal to 0, in that case, this conditional probability mass function is not defined. Right? There's no point of talking about when x equal to simple x, if x cannot be equal to simple x, right? So therefore, in that case, conditioning on the fact that x equal to simple x will not be a meaningful thing to do, right? So this is the definition of the conditional probability mass function of y given the value of another random variable x. Both random variables x and y are discrete in this case. So let's look at an example. Consider the experiment of tossing two tetrahedra. Let capital X denote the number on the downturned face of the first and y the larger of the downturned numbers. Right? You are tossing two objects tetrahedras. X be the number comes up, turned down, number turned down on the first tetrahedra. Y is the maximum of the two turned down numbers. What is the density of y given x equal to 2? So the question is, actually in this case, even though the word density is used here, we are really looking at the mass function because x and y both are discrete random variables. X can take values from 1 to 4, y can take values from 1 to 4. Right? So what we are really looking at is what is the uh, conditional probability mass function of y given x equal to 2. So here I have given the joint probability mass function of x and y. Right? You can easily get these expressions, right? And thereby you can have the marginal probability mass function of x and marginal probability mass function of y. Right? So thereby we can talk about the conditional distribution, right? For example, if we can talk about the conditional distribution of y given x is equal to 1, right? So in that case, we are looking at these probabilities, but of course, the conditional probability mass function of y given x equal to 1 itself has to be a probability mass function, right? Separate, complete probability mass function. So if you add these probabilities, they don't add up to 1. No? So therefore, if you consider these numbers, they do not give you a mass function. So they cannot be considered as the values of the uh, conditional probability mass function of y given x equal to 1. Right? So in order to make the masses adding up to 1, you'll have to normalize them, right? So that the values, when you add the values of the mass function, in this case, the conditional probability mass function, when you add them, you should get 1 to make it a probability mass function, right? So that's why we have to divide these probabilities. These are the joint probabilities. So you have to divide these joint probabilities by the marginal probability. Then if you divide everything by 4 over 16, the conditional probability of y equal to 1 given x1 is equal to 1 over 16 divided by 4 over 16. Conditional probability of equal to 2 given x equal to 1 will be 1 over 16 divided by 4 over 16 and so on. So when you add those four numbers, they will add up to 1. Right. So that's why actually we have this definition here. Right. So this is the joint probability, but in order to make it a mass function, you have to divide by the marginal distribution. The same idea uh, we used when we talk about the conditional probability, right? So we divide this by, because we are looking at the conditional event B, right? So in this case, actually, when you're considering events, B becomes our new sample space. So that's why you are dividing it by probability B to normalize. the sum of the probabilities then will be equal to sum of all the events given B has happened will be equal to 1. Right? The same idea happens here. Right. So, therefore, I can write down probability, conditional probability mass function of y given x at 1, 2, right? For example, I'm considering x when x equal to 2 case here as an example, right? So for you can talk about the probability mass function of y being equal to 1, conditional probability mass function y being equal to 2, equal to 3, equal to 4, given x equal to 2, right? So y doesn't become 1 when x equal to 2, right? You can see that, right? When x equal to 2, we are now looking at this row here. So y doesn't become 1 when x equal to 2, right? So therefore that probability is 0, right? Then conditional probability y being equal to 2 given x equal to 2 is given by this expression. So joint probability divided by the marginal probability of x. So this answer. And similarly, these values can be calculated separately in this case to get this expression for the conditional probability mass function of y given x equal to 2. So here the value at which we are calculating this function is y. So depending on y, this probability is different, right? So when y is equal to 2, this conditional probability is 1 over 2. And similarly, we can talk about conditional probability of y evaluated at some value simple y given x equal to 3, for example. In that case, we'll be looking at this row here, but these probabilities, these joint probabilities have to be normalized by dividing by 4 over 16 to make those numbers add up to 1 and make the conditional probability mass function itself when x equal to 3 is a separate mass function. Right. Okay, now we come to the continuous case. Let x and y be jointly continuous random variables with joint probability density function fx comma y evaluated at xy and the marginal probability density function of x being fxx. And very similar to the previous situation, we are going to talk about the conditional, right, probability density function of y given x is equal to simple x. In order to define that, the density function of x evaluated at simple x should be non-zero. It should be a positive value. Then the conditional probability density function of y given x is equal to simple x is defined as this very similar idea. But of course, these are not probabilities now, they are probability densities. So this is again the notation. Here I have actually used the second notation, right? Remember, sometimes people write down this as this also, f y and then vertical stroke like this and then y x. So in this notation, yeah, here I have used the same thing, right? Because people use different notations, so I have written down that. Right? Sometimes in this note also, I have used this or this depending on the convenience in the situation. So you have to understand that both are the same, right? So conditional density function of y evaluated that simple y given x is equal to simple x. I prefer this notation actually because this is just the notation for the function. This is the value where we evaluate it, right? But this is also commonly used. So it is defined as the joint probability density function of xy evaluated at xy point divided by the marginal density function of capital X evaluated at simple x. And we need this to be non-zero for that to be defined, right? So it's very clear, I guess. But one thing you have to remember is that this is not directly giving you probability. This is similar to the marginal densities that we have discussed earlier. They are density functions, right? Here, x is treated as a fixed value, but thus f, that is the f of y given x is equal to simple x, this whole thing is the label. Evaluated y is a density function in the variable y, in the variable, actually variable capital Y, mathematical variable simple y here, right? Random variable is capital Y, but here, of course, this is the label of the function. In that case, as a mathematical function, variable is y, mathematical variable. It's not a random variable. Simple y is the mathematical way. It's a function of simple y. In this sense, the conditional probability density is obtained by fixing x in the joint density and then normalizing by the marginal density fxx, right? So as I mentioned here, because if you add these probabilities, then if you integrate this joint density over x, it doesn't become 1, right? It's not going to be 1. If you double integrate the joint density with respect to x and y both, then you will get 1, right? But if you only integrate this with respect to x, or if you integrate with respect to y, they are not going to give you 1, right? So here, in order to normalize, we have to divide by fxx. So that's what we have done here. And you can see that whenever fxx is equal to 0, of course, we set the density function to be 0, right? So that means if x is equal to 0, now remember this is not the probability. So fxx can be 0, but in that case, we define the conditional probability density to be 0, right? uh, to comply with fxy is equal to 0. Uh, Geometrically, the conditional density function fy given x is equal to x evaluated at y is the profile of surface fxy cut through the plane parallel to the yz plane passing through the point x0, 0. That is, if you consider as in the three-dimensional plane, divided by fxx. So what does this mean? This is actually the explanation of the geometrical picture, right? What we are saying is conditional density function f y given x is equal to x is actually what you will get if you cut the uh, joint density surface through vertical plane at x equal to simple x. You will see, if you look at from the side, you will see a curve, and if you integrate that curve, you will get the area under the curve. But that curve is not going to, that area is not going to be equal to 1. Right? So the conditional density is actually that curve divided by the marginal density function of x. By dividing by that, then we are normalizing the density function to get the area under the joint density function, conditional joint density function to be equal to 1. So in order to see this, we will look at this picture, right? So suppose this is the surface, joint density surface of x and y here. It's like I have considered like a bivariate normal distribution. Let's now consider the situation. I want to look at the conditional distribution of y given x is equal to some value. So this is the x-axis, this is the y-axis. Z-axis actually shows the joint density function. Z is equal to the joint density function fxy, xy. Right. So if I cut this surface vertically at x equal to 0, right, we will see this blue curve when we look at from this side. We will see this blue curve. Right? So that is actually going to be given by fxy. For example, if we cut this at value x naught, if the value at this x equal to x naught, then what this curve will be fxy x naught y. X naught, x is fixed at x naught, by y is changing. Right? So that will be the curve fxy evaluated at x naught y, if this value here is x naught. Right? But that area under that curve is not equal to 1. Right? But that's what we want to look at. Conditional distribution of y when x is equal to x naught. But in order to make it a complete density function, we have to normalize it. So that if you integrate that function, we have to get the answer 1. If you integrate over the whole set of y values, then we need to get 1. Right? So therefore, we have to divide the density by this area here. That area is equal to, well, not the area. We'll have to divide by each point. We'll have to we here the density we'll have to divide by the density of x at x naught. Right. So then when you integrate that normalized density, conditional density, that will be this red curve, right? After you divide this density by the height of the marginal density, you already know how to get the marginal density here. Marginal density will be the integration of this function, right? That means the area of this. Right? So that will be the marginal. When you divide that by the marginal or the area under this thing, you will get this function. So the area under this curve will be equal to 1. So therefore, this is the conditional distribution of y, conditional density function of y, given x is equal to some value simple x, for example, x naught. Right. So we can easily prove that when you divide this function by the marginal and integrate that, you get 1. Right. So we will see that. Right. The area under the conditional density is 1 because, right, this is the joint density at x, and then if you divide by the marginal, this is what you get as the conditional density. So if you integrate this conditional density with respect to y from minus infinity to plus infinity, this is what you get. You are integrating with respect to y here. This is completely a function of x only. Therefore, you can take it out of the integration. So you are integrating this thing with respect to y. The joint density is integrated with respect to y. We know that is actually the marginal distribution of x evaluated at simple x, right? Here I have forgotten to write down capital X, capital Y subscript, right? But it's obvious, I think it's clear. So this will be the marginal fxx, so this will cancel out, therefore we'll get 1. Right. Okay. So I hope now it's clear to you what we mean by the conditional probability mass function and what we mean by the conditional probability density function. Right. Now, to understand this, we will look at an example. This is coming from Demidenko's book. In his book, this is example 3.21. Right. Actually, what we are going to do here is to look at a way to generate some observations from a given joint density function. Right, we know that joint density is equal to the conditional density is equal to joint density divided by the marginal. So using this idea, what we are going to do is we are going to generate some data from a given joint density using the conditional distribution and the marginal distribution. So we'll be considering certain joint density from which we want to get the data. But we don't know how to get the data. We have to generate X, Y points, right? One observation will be a pair of values, X and Y, right? So we don't know how to generate those XY so that those XY points can be considered as coming from a given joint density. So through this example, I'm going to give you a method for that. The example that we consider is somewhat simplified version, but you can apply the same idea for any other situation. So what we need here is we need to find out the conditional distribution of one variable given the other variable, as well as the marginal distribution of the given variable, right? So the conditional distribution will be a conditional distribution function will be a function of a single variable in that case, single. So it's easy to generate data from that distribution. Marginal distribution is also a function of a single variable. So it's easy to generate from that also, right? So instead of directly generating data from a bivariate distribution, we are going to generate data from two univariate distributions. One is actually a conditional distribution, but it is univariate. The other one is a marginal distribution. It's also univariate. So generating data from univariate distributions are easier. We already know, for example, we have discussed one method called probability integral using the probability integral transform, inverse transform, right? So that's the idea that we are going to look at here. Right. The uniform distribution on the triangle AB is equal to 0.00 point, B is 1A point, where A, we are going to consider A as unknown value at the moment, but we can change, we can give the value, right? We are not going to fix that value. And C is going to be 1, 0. So A is going to be kind of a variable in this case, where A is a positive parameter, right? But we have to specify that if we want to really generate the data, right? But A can be a different situation for a different person, different situation. Find the marginal CDF of X and the conditional CDF of Y given X given X is equal to simple X. Generate and plot n equal to 10,000 random points on the triangle as A with A as an argument in the R port. Right. So for a fixed given value of A, we are asked to generate the data. So, but first, it's asking to calculate the marginal CDF of X. That is the cumulative distribution function. And also the conditional CDF. The reason why we are going to look at the CDF is actually, if you remember, when we discuss about this inverse CDF method or probability integral transform method to generate data from a given distribution, what we needed was the CDF and the inverse CDF. So that's why we are going to look at CDF first. So therefore, we will first get the CDF of X and the conditional CDF of Y, right? Given X is equal to simple X, and then we will generate the data using those two, right? So here is the domain of the joint density, or actually this is the support, right? Support is the set of XY points for which the density function, joint density function is non-zero, right? So in this case, this is talking about ABC, consider a uniform distribution on the triangle. So what we want is to generate data from a uniform distribution defined on this support here. Support is a triangle 0, 0 point, 1, 0 point, and this is 1 A point. A is, in this case, for the another situation, maybe A is 3. Another situation, A may be 1.5, right? Okay. So in that case, this is triangle. This line is y is equal to ax line. This is just y is equal to 0. This is x equal to 1 line. We want to generate data from a uniform distribution defined on. So first thing I want is the marginal distribution of x, right? So we'll have to consider the marginal distribution of x. So what will be the height of the joint distribution in this case? Height of the, because it's a uniform distribution, is going to be a flat surface defined over this triangle, right? So what it we know that the volume under the joint uh, density function has to be 1, right? So therefore, what should be the height of the joint probability density function? It should be calculated so that the volume is equal to 1, right? So we notice that the area of the support is equal to A over 2, right? This is height is A, length here is 1. So therefore, the area of this triangle is A times 1 divided by 2, that is A over 2. So therefore, the height of the joint density function should be then 2 over A, so that the volume will be equal to 1. So therefore, the height 2 over A, where x is between 0 and 1, and y is between 0 and A times x, right? So at this point, x is equal to 1. So y will be 8, y times, y will be actually A, A uh, for a given x, y will be from 0 to 8. For a given x, y will be between and A, because x goes to 1, right? Next, y will be between 0 and A times x, right? So now let us consider any value x in the interval 0, 1, because x can be any value between 0 and 1. We will now expression for the cumulative, no, cumulative at of simple x. By definition, this is equal to the probability that x less than or equal to simple x. So if you consider, we are looking at is actually the volume under a certain, for example, considering simple x value, simple x that x less than or equal to simple x that we are considering here is here. So that the volume under the joint density over the, so that will be equal to actually the height of uh, the density function, joint density, times this. So x here, and when x is equal to simple x, y is equal to ax. So therefore, the area will be ax times Sorry, there was a power disconnection or something. My internet went down. So we were discussing about this problem. We wanted to get the marginal distribution, the cumulative distribution function of x, right? So the cumulative distribution function of x uh, evaluated at simple x is given by probability x less than or equal to simple x. And as I was explaining, I'm looking at this particular, this is the support of my joint density function. So if you consider a particular x value here, right, we want the probability that x less than or equal to simple x, that is equal to the volume under the joint density function over this triangle here, right? So the joint density is a flat density function. So therefore, the volume is going to be that height of the joint density times the area here. The area is equal to x times this length. And here, when x is equal to simple x, y is equal to a times x. So ax divided by 2, so that will be the area of this triangle. And then you have to multiply that by the height of the density function, which is equal to 2 over a, right? So therefore, that's equal to ax square divided by 2 times 2 over a, which is equal to x square. So therefore, the CDF of capital X evaluated as simple x will be given by x square when x is between 0 and 1. So this 0 and 1 here at the beginning and the end of course are always trivially, they are 0 and 1 starting with all CDFs are starting with 0, ending with 1. So when x is less than or equal to the lower limit here in the support, it should be 0. And when x is above the upper limit of the support, the CDF should be equal to 1. So this is the CDF, and this is the part that we are interested in. Uh, uh, so using that, this can generate the data from the distribution whose CDF is equal to x square, right? Suppose I want to generate data from some distribution whose square, right? So we know that how to do that, right? We know that this is also discussed in a previous lecture. If you calculate the cumulative distribution function at a certain random variable, that new random variable has a uniform distribution between 0 and 1. We have proved this thing. This is an important result. So if I denote, for example, this fx simple x that I calculated here by simple u, because fx simple x is a number, not a random number. Let's therefore denote it by u. So u is equal to x square in this case. So x will be equal to square root u. That will give you the inverse of this fx. So inverse of x, f inverse x evaluated at u will be equal to square root u. F inverse, fx inverse u evaluated at u is equal to square root u, right? So therefore, if you get some data from a uniform distribution, right? Suppose this u is uniform now, uniform distribution is 0, 1. And if you get the square root of those values will have the CDF given by this function here. So that's what we mean by the inverse CDF technique to generate data from a given distribution with a given CDF, right? So we have to find out the inverse of the CDF from which we want to get the data and then get some uniform 0, 1 data and transform those uniform 0 data using that inverse CDF function. Then the resulting values will have the CDF, the required CDF, right? So if I want to generate the data from that particular CDF, that is the method. Then x equal to square root u will have the CDF of fxx, right? Now we are going to look at the conditional CDF of y given x is equal to some value simple x, right? Conditional CDF, right? So that is will be denoted by capital F y given x using the same notation previously, but we were discussing the density. Now we are discussing about the cumulative distribution function. So by definition, this should be equal to probability y less than or equal to simple y given x is equal to simple x. Right? Going very parallel to the previous definitions, this is the definition for the cumulative uh, conditional cumulative distribution function of y given x is equal to simple x. Right? So this we can obtain by integrating the conditional distribution function of y given x with respect to x. Because we want probability y less than or equal to simple y, the integration should be in this particular case from 0 to simple y, right? Because y is uh, between 0 and a. But in this case, we want less than or equal to y value, therefore up to y. Here, I'm changing the variable of integration. Otherwise, here what we have to do is we have to integrate actually with respect to y. But if I put y here and y here, because limit also has y, that will be a little bit confusing. So therefore, I have changed the variable of integration to be v, right? Just to use some other letter different from y, right? But we are actually integrating with respect to this y here, right? So this is what we want. F y given x integrated with respect to y, and then putting the limits from 0 to y. Right. So in order to get this expression, right, we need the conditional density. So we will use this definition, original definition, conditional density of y given x is equal to simple x is the joint density divided by the marginal. We have already found out the marginal, therefore we can get this expression. So when we get that one, got was the not the marginal actually. If you won't get the marginal, you can just take the derivative of this one. This is the CDF, right? So if you want to get the marginal, you could have obtained it by just taking the derivative of this thing. So that will be 2x. But here I'm just using the definition, right? So from that also I'm getting 2x, right? So if you the other way to get the marginal is integrate the joints. We have to because we are calculating this thing at x, in that x, at that x, y will be equal to ax. So therefore, we have to integrate with respect to y from 0 to ax, and that will give you 2x, right? So this is the long way here. Once you have obtained already the CDF, you could have just taken the derivative to get the fx. So therefore, the conditional density function will be equal to the joint density 2a divided by the marginal 2x. So that will be this one. So therefore, now I get the conditional CDF, right? That's what we wanted here. The conditional CDF was is equal to integration from 0 to y, the conditional density. So therefore, the conditional CDF is equal to integration from 0 to y of this function 1 over 2x with respect to dv. This is the answer you're going to get. Right? So notice that this is a function of y and x both. That we are evaluating this function at y, but for a given x equal to simple x. So that is the uh, distribution of y given x is equal to x. Right. Now, if I want to generate data from this conditional distribution, do is I have to find out first of all the inverse of this function, and then take some uniform random numbers and transform those uniform random numbers using that inverse CDF. Then the resulting values will be numbers coming from this particular conditional density function. Right. So this is the conditional density function of y given x equal to simple x. Again, this is the important part. Trivially, the starting values will be 0, and after the support, maximum value of the support, it will be equal to 1. Right. This is the usual form of any CDF, starting with 0, ending with 1, of course, and then there will be, in this case, in the middle, there is a region where it's non-zero or not equal to 1. Right. So I have mentioned here, I have, for example, considered the inverse of this function. Right. Inverse of that function will be given by a times u times x. Because if you consider this thing to be with a simple y to be, for example, u, right? We say let's u be equal to this thing evaluated at some simple y. In that case, it's going to be simple y divided by ax. So let's say u is equal to y divided by ax. Then y will be equal to u times a times x. So therefore, that will be the inverse function evaluated at u. Right. So y is equal to inverse of this function evaluated at u given x. That is equal to AUX. Right. So now if you take some uniform random numbers and transform those uniforms will be denoted by this U, right? And A will be a given number, X will be a given value also. So for a given simple X and given simple A, take some uniform random numbers and then calculate A times U times X. So we'll have now new values, some random numbers. Those random numbers will have this CDF, right? Now, how do we generate the data from the joint density that we want in the density function defined on a triangle? How do we generate those XY points? Using these two CDFs. One is the marginal CDF, the other one is the conditional CDF. Right. So, using the marginal CDF of x, first of all, we can generate some random number simple x coming from that marginal density of x. Right. Starting with uniform, transform that uniform random number using the inverse of the marginal CDF, and the resulting value will have the density function of x. And then with given that x, we can generate a y value with a given a, of course. Without giving a, we cannot do this. So for example, let's say a is equal to 2. So if a is equal to 2, now we have obtained x, generated the x using the marginal distribution of x, actually using the inner CDF of x. We have obtained a x value. So put that x value here, and then a given value like 2, and then get some uniform random numbers, right? And then those values with a times those random numbers and that particular x that we generated, we will get set of y values. Those y values can be considered as coming from uh, this particular marginal density function. No, actually, yeah, marginal density function. And if you now consider uh, the pair xy can be considered as an observation coming from the joint density that we want, right? So that way I have to do 10,000 times if I want 10,000 pair of observations coming from the given joint density, right? So the procedure to generate 10,000 random numbers will be like this. Generate, uh, in here I'm explaining how to do it for one random number, but you can do it 10,000 values at the same time very easily in this case. So generate a random number u1 from uniform 0, 1, or you can directly generate 10,000 random numbers from this uniform 0, 1. So let's call that vector, for example, u1. And then calculate x equal to square root u1. So for all those numbers, calculate square root u1. So those numbers now can be considered as coming from the marginal distribution of x that we require. And then independent to these things, now separately starting again, generate another 10,000 numbers from uniform 0, 1. Let's denote that vector by u2. X values in this vector calculate a times the u2 values, right? So individual observations in the vector and x vector will be now multiplied, thereby you will get, right? And then those pairs of x and y values, x vector will contain 10,000 values, y vector will contain 10,000 values. So now you have 10,000 pair of xy points, and those can be considered as coming from this particular density that we want the data from, joint density. Right. So if you just consider the one observation, this is the uniform 0, 1, and transform it using this transformation, take the square root and call it x, right? And then independently generate another random number from a uniform distribution, uniform 0, 1, let's call it u2, and then calculate this one, y, let's call it y is equal to a times this x times 2, and let's call it y. So you have x value and a y value. Now, if you consider these two as a pair, that will be an observation coming from the joint density, uniform joint density defined on the triangle, right? So that is the way to generate. That is one way actually we can use to generate data from a given joint density. So what we need here is the marginal density function and the conditional, actually what we need is the marginal CDF, because we need the inverse of that to generate the data from X, and then marginal CD of Y given X to generate data from the marginal distribution. I made a mistake. What we need is the conditional density of Y given X equal to simple X. Conditional CDF, right? And that will be required to get the data from that conditional CDF. Once you have those two, then the pair can be considered as coming from the joint density function. Right. So here is the function that I used. It's very simple actually. At the beginning, some checkers to see whether n is a acceptable number and a is an acceptable number. In this case, a has to be greater than 0, right, and so on. So this is the procedure. U1 is I'm generating, in this case, n. I'm going to consider, for example, 10,000. In that case, 10,000 random numbers from uniform 0, 1. U2 is another set of 10,000 values from uniform 0, 1. So x is equal to square root of u1, y is equal to a given value a is an input of this function, a times this set of x values. Here we have a vector of x values times the u2. So that's y, right? So therefore now you have prepare a data frame. So that data frame will contain xy pairs of observations, 10,000 pairs of observations coming from the required joint density function. Okay, I think that is a good point to stop uh, this part of the lecture, and we will continue from there in the next lecture. In the next lecture, we will start with the independence, definition of independence in terms of the conditional density and the marginal density. We already know the one definition of the conditional, one definition of the independence of two random variables x and y expressed in terms of the joint probability density function or the mass function and corresponding marginals, right? In that case, we said two random variables x and y are independent if and only if the joint density or the joint mass function is equal to the product of marginal densities or the product of marginal mass functions. And here we are going to look at another definition. We will discuss that in the next lecture.